Hello students, today let us discuss the topic ultrasonic testing, which is one of the methods of non-destructive testing. So first of all, let us know when this technique can be used. So introduction to ultrasonic testing. So this technique is used for detection of internal and surface, particularly distant surface defects in sound conducting material. So we have to note that this technique is used only when the material is able to conduct sound through it. Internal and surface, particularly distant surface defects in sound conducting materials. So sound conducting materials. So the principle of working of this ultrasonic testing is almost similar to that of echo sound. So here principle is in some respects similar to echo sound or echo sounding. So what is done in this ultrasound? So a short pulse of ultrasound is generated by means of an electric charge which is applied to piezoelectric crystal. So when electric charge is applied to piezoelectric crystal, then short pulse of ultrasound will be generated. So this piezoelectric crystal will vibrate for a short period at a frequency which is related to the thickness of the crystal. So here short pulse of ultrasound is generated by means of an electric charge applied to a piezoelectric crystal. The crystal vibrates for a short period at a frequency related to the thickness of the crystal. So in flaw detection, usually the frequency which is used is in the range of 1 million to 6 billion times per second. That is 1 megahertz to 6 megahertz. So in flaw detection, frequency used is in the range of 1 megahertz to 6 megahertz. So at this frequency, the sound waves or the vibrations have the ability to travel at a considerable distance in homogeneous elastic material such as many metals with little attenuation. So at this frequency, the sound waves can travel a long distance in homogeneous elastic material. So the ultrasonic energy is considerably attenuated in air, and a beam propagated through a solid will on reaching an interface. So example, if there is a defect, or if there is any hole, or there is a blockage, then what happens, this ultrasonic energy will be attenuated in the air, and there will be a beam propagated. So a beam will be formed when this energy or this rays reaches any defect or any hole which is present between the material. Okay, and the air will deflect this energy, considerable amount of energy, in the direction equal to the angle of incidence. So for example, now if this is a component and if there is some defect here, so what happens is, when the ultrasonic rays are made to fall on this material, so they will travel inside the component. When they encounter any defect, then what happens, the air which is present here between the rays and the material will reflect a considerable amount of this energy. So these rays will be reflected back in the direction which is equal to the angle of incidence. So here it will reflect back the energy, and this can be received and can be measured. So ultrasonic energy is attenuated in air, and a beam is propagated through a solid wall, and on reaching an interface. Example, a defect or hole, etc., between the material and air reflect a considerable amount of energy in the direction equal to angle of incidence. So what, to simplify this operation, what is done is, the contact testing, the oscillating crystal is incorporated in the handheld probe. So you might have seen there is ultrasound testing done if the doctor suggests that if there is any problem with your stomach or any part of your body, so ultrasound may be done. So in ultrasound, what they do is, there is a device, something like a handheld device is there, something like this. So in this device, the crystal will be incorporated, and it is moved on your stomach to check your internal problems. So between this device and your body part, there will be some liquid, they will apply some liquid. So this liquid will facilitate the energy transfer across the air gap which is present between the crystal. So here air gap will be there, it will not allow the energy to pass, or the movement of this crystal, that is the oscillating crystal's energy will not be passed through the part of your body. So that is why small amount of liquid is applied here, so that it will facilitate passage of energy across the small air gap between the crystal and the test piece. So that liquid which is applied is called as cupellant. So usually while testing the material, cupellant is used, and that cupellant is oil, water, or greased. So contact testing for both the human body and material is done with the same procedure. So for contact testing, transfer of energy across the small air gap between the crystal and the test piece. A liquid is applied, a layer of liquid is applied, that is the cupellant. So which is usually oil, grease or water. So the crystal does not oscillate continuously but in short pulses between each of which it is quiescent. Okay, so this crystal is not oscillating continuously, it will oscillate in pulses. So it will oscillate for some time and then it will be remain quiescent. So quiescent means it will remain inactive for some time. So these piezoelectric crystals not only convert the electric pulses to mechanical oscillations, but they will also transduce mechanical oscillations into electric pulses. So piezoelectric crystals not only convert electric pulses to mechanical oscillations into electrical pulses. So they not only generate sound waves but they also detect the returned pulses. So these piezoelectric crystals, piezoelectric crystals not only generate but also detect the returned pulses. So when the crystal is in the state of quiescent, that is when it is inactive, it will detect the returned pulses. So when the piezoelectric crystal is in a state of quiescent, then it will detect the returned pulses. So these pulses will take some time to travel through the material and to the interface and then be reflected back to the probe. So these pulses take a finite time to travel to the material interface and return back to the probe. So the standard method of presenting the information in ultrasound testing is by means of a cathode ray tube. So in this method, the horizontal movement of the spot from the left to right will represent the time elapsed. So the standard method of presenting information in ultrasonic testing is by means of So this spot is moving from left to right. So the ultrasonic testing is shown, the information which is collected by the ultrasonic testing is shown with the means of this cathode ray tube, and this cathode ray tube has a spot. Okay, so the horizontal movement of this spot from left to right will represent the time elapsed, and this spot is moving so fast that it gives appearance of a horizontal line on the screen. The rate at which the spot moves is such that it gives appearance of a horizontal line on the screen. And this system, that is the cathode ray tube and the ultrasound testing equipment, are synchronized electronically so that the instant the probe receives the electric pulse, the spot begins to traverse on the screen. So the cathode ray tube and the probe, that is nothing but this is the probe. Okay, and there is a cathode ray tube, and they are synced, or they are connected to one another in such a way that when the probe moves on the material, the spot which is handled by the cathode ray tube starts moving on the screen. The spot moves on the screen. So an upward deflection, that is the peak of the line on the left hand side of the screen, is indication of this occurrence. That is nothing but if there is a peak on the left hand side of the screen, then that will indicate the initial pulse. Indicates the initial pulse. So when the baseline is perfectly level with the crystal, perfectly level, that is when the baseline is level, that is it is touching the bottom of the screen, then the crystal is quiescent or it is inactive. So when the baseline is perfectly level, the crystal is quiescent, that is nothing but it is inactive. So any peaks to the right of the initial pulse indicates that the crystal has received an incoming pulse deflected from one or more interfaces in the material. So if there are any peaks on the right hand side of the initial pulse, so this is the initial pulse, and we can see there are peaks reflected back from the probe. So that is indicating there is a flaw, or there is an interface, or there is some detection of discontinuity in the component. So any peak right of the initial pulse indicate that the crystal has received an incoming pulse reflected from one or more defects or interfaces in the material. So here there is the flaw echo. So since this spot moves at a very even speed across the tube face, and the pulse of ultrasound waves moves at very even velocity through the material, we can calibrate these horizontal lines into absolute measurements. So the spot is moving across the tube face, that is the cathode ray tube face, okay, and it is moving at a even speed across the tube face, and the pulse from the probe is moving at a very even velocity through this material. So we can calibrate these horizontal lines into absolute measurement. That is nothing but, in simple words, we can make absolute measurements by using these horizontal lines. Since the spot moves at a very even speed across the tube face, and the pulse ultrasonic waves moves at a very even speed or velocity through the material, it is possible to calibrate the horizontal line on the screen in terms of absolute measurements. So the screen can be calibrated, or the lines can be calibrated in terms or units of distance, and therefore determination of origins of the returned pulses obtained from the test piece can be calculated. So these lines or the horizontal lines can be converted or calibrated into absolute measurements. So in units of distance we can calibrate this screen. So what happens by calibrating screen in terms of distance? Then we will be able to determine, or we will be able to find out the origin of the returned pulses obtained from the test piece. So this probe will send a signal and it will receive a signal, okay. So the origin of the received signal, or the place from which it is received, so that distance can be calculated from this screen. So that is why it is not only possible to detect the defect which is present in the component, but also we can measure the distance at which this defect is present, or distance at which below the surface. So if this is the surface of the component, so we can calculate this distance at which this defect is present. So by this we can not only discover the defect, but also we can measure its distance below the surface. So it is important that the equipment is properly calibrated, and since it is in itself not able to discriminate between the intended boundaries of the object under test and unintended discontinuities, the operator must be able to identify the origin of the peaks. So this instrument will just give us the peaks. So we have to, the person who is operating or who is using this method must be able to discriminate, or he must be able to understand what are the peaks or the origin of the peaks indicating. So probing all the three surfaces of the material, or see, if after you finish probing here, that is after you finish moving this probe on this surface, you can move it on this surface and this surface. So all in the three-dimensional directions, when we have probed the faces of the test piece, we can not only discover the defects and measure its depth, but we can also determine the size of the defect. So probing in all faces of test piece not only discovers the three-dimensional, I'll just write it as 3D defect, and measure its depth, but can also determine the size of the defect. So here we can see there is a diagram which is showing use of an angle probe to detect defects not directly under the probe, such as in weld inspection. So in welding inspection, we may find some defects are present which are not. So for example, if you are not able to reach this surface, this part of the surface, you cannot probe it. So in that case, what is done is angle probe is used. So this angle probe will detect the defects which are not directly under the probe. So interpreting these indications on the screen will require some amount of skill when the testing is done with the handheld probes. So it will require interpretation of the indications on screen, requires a certain amount of skill when testing with handheld probes. So the technique is, however, admirably suited to automatic testing of regular shapes by means of a monitor and electronic device that fits the main equipment to provide an electrical signal when an echo occurs in the particular position on the trace. So here ultrasonic testing can be automized, but only for regular shapes, okay, by using a monitor and an electronic device which will provide the electrical signals when the echo occurs in the particular position. So the trigger level of this signal is variable, and it can be made to operate a variety of mechanical gates and flaw warnings. So furthermore, improvements in computer technology allow the test data and the results to be displaced and outputted in wide variety of formats. So this can be automated, this technique can be automated, and with the help of computer, the results can be displayed in different formats, okay. So the velocity of sound is varying in different kind of material. So the velocity of sound in steel will be different, and the velocity of sound in copper will be different. So this method depends on the velocity of sound in any material, and it is the characteristic of that material. So that is why it follows some materials can be identified by determination of the velocity. So I will just write down the important point, that is this method can be automated and is now being used in many foundries. So when the velocity is constant as it is in the wide range of steel, so in steel the velocity is constant. So in such cases the time taken for the pulse to travel through the material is proportional to its thickness. So the time taken to travel by the pulse is proportional to the thickness of the material through which it is traveling. So this can be applied only when the velocity is constant. So this is applied when velocity is constant. So these equipments are easy to use, but it requires prudence in their application. So now, what are the advantages of ultrasonic flaw detection? So the first one says that thickness and the length up to 30 feet can be tested. Thickness and lengths up to 30 feet can be tested. So position size and type of defect can be determined. So with the help of ultrasound, not only the position size but the type of defect also can be determined. And here we get instant results. So instant test results are obtained. And this device or the instrument is portable. So we can carry it from one place to the other. So it is extremely sensitive if required. So if you want to check even very sensitive defects, we can check with the help of this instrument. So extremely sensitive if required. So capable of being fully automated. So as I have already told you, it can be automated. And so in instrument which are already fixed on some component, for example, if we have fixed this instrument on a component and we can test it only from this side, so this ultrasonic testing will facilitate such testing. So access in this kind of testing, access to only one side of the component or the subject which we are testing is necessary. So access to only one side is necessary. And there are no consumables here. Now, what are the disadvantages of this ultrasonic testing? So here no permanent record available unless one of the more sophisticated test results and data collection system is used. So no permanent record of the testing or the result is not available. So if you want permanent record of the result, you will have to use some sophisticated data collection or result recording system. So here the interpretation or the person who is operating will have to have very high degree of skill to obtain the full information of the test. So considerable amount of skill is necessary to obtain the full information or fullest information from the test. So if a layman is going to just see the results of this test, he will not be able to understand what they are actually showing. So very thin sections prove difficult to be tested. So very thin sections cannot be tested with the help of this ultrasonic testing. So indications require interpretation. So whatever is indicated on the screen must be correctly interpreted. So the last disadvantage is that the operator can decide whether the test piece is defective or not while the test is in progress. So this is all about the introduction, principle of working, the actual working, the testing of the ultrasound, and the advantages and disadvantages of ultrasonic testing, for which is a method of non-destructive testing. So I hope you have understood the topic. Thank you.